Okay, so the recording is going. Today we are talking about section 3.5. I think I misspoke last time and said that we were only going to cover 2 sections, but in fact, we'll cover only 2 sections in the lecture, but there are 3 sections due in the homework. So you still have 3.6 that's due this coming Monday. And the main reason that I'm not going to lecture over it is that we've already pretty much covered all of the topics in that section. And the way the book is built is that if you'd like to skip some earlier sections, they have it built in so that you can cover them sort of later on. And this is an example of one where you already have all the material. We've talked about it in previous sections, so I don't think there's anything I need to say. But we will have a review session on Monday, so if you have questions about that section, you can sort of ask at that time. There are only 9 questions. They're pretty straightforward. However, for section 3.5, on the other hand, there are 30 questions. And so you should get started on this section as soon as possible. If you haven't done so, you should get started this afternoon. A lot of them are multiple choice questions, but there are a lot of questions there. Okay. So we're talking about function transformations. A little bit more too about the course. So right now, we've got basically 2 more sections to cover in terms of the midterm. And that's going to be section 3.7, where we talk about inverse functions, and then section 4.1. If you're following along in the syllabus, we said that we'd cover 4.2, but we're going to omit 4.2 from the midterm exam. And what that means is that next week, after we cover those 2 sections, we'll have covered all the content that will appear on the midterm. Then we'll have 1 more week before the exam, and we'll do reviewing, and I'll give you more context about the exam. We'll have some practice exams. And I won't cover any new content, but we'll be here in class doing practice problems, and you can ask questions about old homework assignments and various things like that, maybe old quizzes, anything that you might want to ask about. And there'll be some practice problems and things that we'll work on at that point. Okay, so what we normally start with here is our objectives. So let me put those up on the board here. Today we're talking about transformations of functions. So we should have a sort of basic idea of the shapes of functions like x squared, the square root function, the absolute value function, and we had those back in section 3.1. And now what we're going to do is take those and shift them around. So we're going to move them up and down, we're going to move them left and right, we're going to stretch them and squeeze them both vertically and horizontally. And there's a nice set of algebraic techniques that allow us to apply algebraic stuff to the equation, and what we'll see is that then in the graph, we'll see those things reflected as transformations, okay? And we'd like to go backwards, right? Both ways. So if somebody gives you the graph with a sort of transformation, you'd like to write down the equation, or vice versa. Somebody gives you the equation, you'd like to be able to graph it. So there's sort of a 2-way street here. We'll talk first about graphing functions vertically and horizontally with shifts. We'll then talk about reflections, both across the x and the y-axis. So these are sometimes called vertical and horizontal reflections. We'll then use that information to introduce the idea of even, odd functions. And it could be the case that the function is neither even nor odd. They're like real numbers, right? So like the number 1/2 is neither even nor odd. Some real numbers like 1 are odd, some are even, like 2, but something like 1/2 is neither. And functions have a similar sort of trichotomy, so breaking it up into 3 different parts, and we'll use this reflection business to determine if something's even or odd. This is going to be really important for those of you going on to calculus, because if you can recognize something as even or odd, you can exploit that symmetry, and you can save yourself a lot of headache and time in a calculus course by sort of bypassing a lot of the details that you would normally have to use. And then the last thing that we'll talk about, not as important, but there are some questions in infinity, so we need to say something about it, is the idea of a compression and a stretch, right? So here we're not going to add something to the variable, we're going to multiply the variable, and I'll just tell you what it looks like. We won't go into as much detail there. I wouldn't focus too much on it in terms of graphs, or even there's like a scaling constant, but it's not going to be nearly as important. And then along the way, we'll combine our transformations, okay? So we'll look at some examples where we have multiple transformations going on at the same time. Okay, and then as usual, if you guys have a question, this is a good time to ask it, and then as soon as you have this written into your notes, or you're done sort of reading it and you're happy, give me a thumbs up, and as soon as we get enough people, or give me a I'm done or something like this, and then we'll move on. Okay, great. So it looks like a lot of people are done. The first thing we're going to talk about is what's called vertical shifting. And vertical shifting is what happens when you take a function f of x and you add a constant to it. Okay? So you can think about this as being sort of in terms of that picture that we have in our mind, the mental picture of a function. There's an input and an output. What we're saying is throw the input x into the function, let it do its computation, and then get out f of x. Okay? That's what this is. And then once you get the output out of the function, just add k to it. Okay? And the effect in terms of the graph is that you'll simply take the y value, right? So remember, the function output is the y value on the graph here. You'll simply take the graph and either shift it up or down based on whatever the value of k is. Okay, we call that a vertical shift. And if that value of k is positive, then the graph will go up, right? And if the value of k is negative, then the graph will shift down. And that's because, for example, if I started out at this point here, so let's say somebody gives you this function in blue here, f of x, and I'm going to start out at this point 1, 1. Well, if I want to add 1 to this function, then what's going to happen is the y value is going to increase by 1. So the x value stays the same, and the y value is now 2, which is 1 plus 1. So for example, at a different spot, at -1, -1, it goes up by 1. So this whole function here in orange is just shifting the one in blue up by 1 unit. And you can see it a little more nicely in what's called the Desmos. So today we'll be using this nice graphing calculator. We can't use graphing calculators on the exam, but we can use them to sort of hopefully visualize some of the stuff that's going on here. And you can always find this for free at desmos.com. You just type it in desmos.com and you'll open up to this page here. So what you can type in over here are things like equations. For example, we might look at y equals the square root of x. So it's this sort of half parabola turned sideways here. And the nice thing is that Desmos also supports functions. So we could have written this as f of x is equal to the square root of x. And now it knows what f of x is. It knows it's this square root function, right? So I can do things like compute f of 4, and it'll say, the output there is 2, or I could compute, f of 9, and it would say, okay, the output is 3. So it knows what my function f of x is. And then we can do some interesting transformations. So we can do something like f of x, say, plus 3. And again, what's happening now is we're taking the y value and we're adding 3 units to the y value of each point in this graph. And so the graph here in black just goes up by 3 units. Okay, every single point goes up by 3 units, up by 3 units, up by 3 units. And if we were to subtract something here, if we were adding a negative, then it goes down, right? So this is going down by 3 units. So here's -5. And you can see the whole sort of situation if we just put a variable here plus k, thinking about k as a constant. Desmos allows you to add a slider, and then you can slide around the value of k. So when k is negative, like -7.5, we're 7.5 units down. And then when k is 0, we're on the same graph. And then boom, we're going positive again. Okay? So adding k is a vertical shift. And you could do this with any function you would like. For example, maybe you've taken some trig classes, and you might have seen the function sine of x. It's this one here in black. And then we'll shift by 3.2 units up. So we can go up or we can go down, right? So we're shifting up or down. And really, it's just adding on k to the output of the function. Okay. So that's what this says here in a little more detail. Okay, so that's a vertical shift, up for positive, down for negative. Okay, so now we're going to talk about a horizontal shift. And in a horizontal shift, instead of adding on to the y value, you're going to add on to the x value. And I want to point out something here real quickly. So in those cases, we were looking at something like y equals f of x. And if we wanted to shift it up by k, or down by k. K was negative. Then we looked at y equals f of x plus k. Okay? And if I really wanted to move this k next to the y, I'd have to subtract, right? And so I see this is like y minus k is equal to f of x. So really, in the equation, if I wanted to put the k next to the y, I have to subtract the k. And then so if this was negative, it would mean that we were shifting up, and if this was positive, it would mean that we were shifting down. But that's what's happening when we're next to the y. So what you're going to see here in these notes up here is that the book will write it like this: f of x minus h. And when you have f of x minus h, this is a horizontal shift, okay? And I think the book sort of says it in a funky way here. What they say is, okay, well, when h is positive, it shifts to the right, and when h is negative, it shifts to the left. But I think that's sort of a bad way of thinking about it, because, for example, it's really easy to get it mixed up, right? Which way is left and which way is right. Because a lot of the times you'll be given an expression that looks like this: f of x plus 1. And the natural inclination for a lot of students here is that it's going to shift to the right because we're adding plus 1. But that's wrong. In fact, what we're really doing is we're subtracting negative 1, right? And if we're following this template up here, that's what's going on. And it actually matches up with what we had in the previous example for the vertical shift, because if we were to move that k next to the y, it would look like this x minus h. So here, I'll just say, if you add a constant to x, if it's positive, it goes to the left, like this orange one here. So this goes to the left 1 unit. And if it were negative, it would go to the right by whatever that value of the unit is. So let me go back to Desmos and show you that in action, okay? Because it's not really like important about what convention you use here, about if it's h or if it's just adding on h or subtracting h. What's important is that you understand when it goes left and when it goes right. Okay. So here is, I believe, Desmos. No, here it is. Okay, so here's Desmos, and instead of adding the plus k to the outside, we're now going to add the plus k to the inside. And I'm putting it in as plus k and not minus k, because I want to show you sort of what's happening. It's probably best to not use this guy and use instead the square root function like we had before. So here's the square root of x. So the square root of x here is this function in black. And what's happening now is the k here is negative 1.7. So it's x minus 1.7. And what we get is a shift to the right by 1.7 units. Okay, so what I'm saying is that if you saw in the book f of x minus 1.7, you would shift to the right and not to the left. A lot of people feel like this should go to the left, but it doesn't, right? I mean, if you go through the mathematics like we're saying right now, then it's really a shift over to the right. And that makes sense. If I plug in 1.7 into this, it's the same thing as plugging in 0 into this one, because it would be 1.7 minus 1.7, which is 0. Okay, and then if this is positive, so it's x plus 1.7, then the shift is to the left. Okay, so you can see that here as we shift these values around, right? So negatives go to the right, positives go to the left. And that's sort of not exactly the same thing that the textbook says. They say it sort of in this funky way in terms of x minus h, but they're just hiding the negative sign up in the formula up there. I think it's easier to just kind of think about what the sign is. Okay, so let's try and do some examples, okay, to maybe hopefully clarify some of these details. So here's that horizontal shift and the vertical shift. And now let's do this example. Okay, so here we're going to be given that function, the square root of x, and we want to apply a transformation and look at f of x plus 2. Okay, so first off, is it a vertical or a horizontal shift? In the chat, let me know. Is this vertical or is this horizontal? Well, I see there's a mixture of people saying vertical, some people say horizontal. Okay, so we're adding to the x, right? We're adding to the x, and the x is the horizontal part, right? So it's going to move horizontally, not up or down. The up or down would be if we added 2 to the outside. Notice there's a parenthesis here. So this is going to be a horizontal shift. Now, is it a shift to the left or to the right? So x plus 2, it's to the left, right? I mean, it feels like it should be to the right, but it's actually the plus 2 makes it go to the left, and it's going to go by 2 units, right? So the question here is, where does it shift? Well, it shifts 2 units to the left, okay? So let's go ahead and graph it, because that's what they're asking us to do here. And the way you graph this is you start off with this function, f of x is equal to the square root of x. And like I said, that function is half of a parabola. We could plug in a few points. When x is 0, it has a value of 0. When x is 1, the square root of 1 is also 1, so it has a value of 1. When you plug in, let's say 4, the square root of 4 is 2, so it has a value of 2 up here. And it's just a parabola, like half of a parabola turned sideways. So that's the graph of the square root of x. And what we want to do is shift 2 units to the left. Okay? So let me put the whole board up so you can see everything. So you want to shift 2 units to the left and compute what is f of x plus 2, right? Or not compute it, but to give a graph of it. So this point here is going to go from an x value of 0 to what x value? What's the new x value of this point when we shift over by 2? Yeah, so we're going to the left, so it's going to go over here to negative 2, right? So in my new picture over here for this function, this value goes to negative 2. And what about 1? Where does 1 go? If we shift 2 units to the left, where does 1 go to on the x-axis? So 2 units to the left, where do we go? To negative 1, right? So here's 0, and then bang, there's negative 1. And notice the y value stays the same. So there it would be a value of 1. And then here at 4, we're going to go 2 units to the left. That's going to get us to 2. So here's 1, 2, and that goes up to a value of 2. And so we get this parabola like this. And what we have here is the graph of this function shifted 2 units to the left. And we could write down a formula for this, right? We know how to do this now. We have f of x is equal to the square root of x. So everywhere we see an x, we'll replace it with x plus 2. So this is the square root of x plus 2. Okay? And we could have found the domain of this function just using our old techniques. The domain of this function, so the domain of this function would be all the values of x plus 2 that are greater than or equal to 0, right? So we'd say x plus 2 is greater than or equal to 0. We'd say then x is greater than or equal to negative 2. And then the domain would be all the numbers from negative 2 out to infinity. And that makes sense. That's exactly what's going on in this graph here, right? So this is the domain. The domain is all numbers from negative 2 out to infinity. So that matches up with what we had before. And this as well, right? So here the domain of this function is when x is positive or 0. In other words, from 0 all the way out to infinity. And that's this piece down here. Okay. So that's our transformation of this function. And it's shifted 2 units to the left. Okay? So that x plus 2 shifts it 2 units to the left. There's no vertical one because we're not adding to the outside. Now, another way to think about this, right, I should say this before we go on, is that when we were doing the vertical shifts, we were adding to the output of the function. So it was just f of x plus k. But here, notice we're doing sort of something slightly different. We're first adding the constant to the input. So before we put it into the machine at all, we add 2 to the input. And then once we add 2 to the input, then we put it into the machine, right? So then we get this f of x plus 2. So it's slightly different, right? Do we add the 2 at the beginning before we put it into the machine, or do we add the 2 at the end? Okay, so one more example here. This has one where we're combining 2 shifts. as I'm sketching the graph for the absolute value of x, let me ask you in the chat to tell me what the shifts are. What's the vertical shift and what's the horizontal shift? Or is there none, right? It could be the case that there's no shift at all. So let me know if you guys can see this guy with the shift. And as you're doing that, I'm putting up the f of x as the absolute value of x. Okay, so everybody is saying left by 1, down by 3. Yep, that's exactly right. So here's the horizontal shift. It's what's next to the x. We're adding 1, so that's to the left by 1 unit. And then we subtract 3 from the output of the whole entire function, so that's moving down by 3 units. Okay, so here's our graph of the absolute value function. Just as a reminder, you should sort of have this thing sort of committed to memory by the time the exam comes around. But you can always graph it just by picking some points, right? The absolute value of positive things just gives you the same value. So at 1, it's a 1. At 2, it's 2. At 3, it's 3. At 4, it's 4. And that just means it's a straight line, right? With slope 1 and intercept 0 when x is positive. And then when x is negative, it gives back, you know, the absolute value of -1 is 1, of -2 is 2, and so on and so forth. And so that's now aligned with slope -1. And it looks like a big V. Okay? So here's our graph of this guy. And really, when you're moving absolute value functions around, you want to keep track of where this is. Okay, so right now it's at the origin, but we're going to do this shift, right? We're going to shift, and when we shift, where will that origin go? If we're moving 3 units down and 1 unit to the left, where are we going to go? Tell me what the ordered pair is where that guy goes. Okay, yeah, so it's going to the left and down, so it's going to go to -1 and down to -3. So this point goes to the left and then down, right? And the lines are still the same. So this is still going to be aligned with slope 1. So you go over 1, and it's just aligned with slope 1 like that. And then over here, this one is just going to be aligned with slope 1, so it's just going in this direction. And it's just a sketch, right? They're asking you for a sketch here. And this guy, and so here we've got f of x, g of x is equal to the absolute value of x plus 1 minus 3. Okay, we've shifted to the left 1 and then gone down by 3. And so that's what the shift looks like. And this is one where we combine shifts, right? Okay. Here's another one. And I think everybody's sort of got the hang of this, so let's just in the chat ask really quickly, left and right, is this a shift to the left or to the right? This is 2 units to the right because it's -2. And then what about up or down? 4 units up, plus 4. Okay? So instead of taking this down into the left into that third quadrant, we would take it up into the right in the first quadrant. So 2 units to the right, 4 units up. Okay. So it would be somewhere up here. Oh, this guy gets mapped up there. Okay, so that's the vertical and horizontal. So now what we want to talk about is another transformation. And the other transformation we want to look at is reflecting across an axis. Okay? So when you reflect across an axis, what you do is you take an ordered pair like x, y, and to reflect across the y-axis, you replace the x value with its negative. Okay? So if you started with some point here on you started with some point here in the xy plane, and you wanted to reflect across the y-axis, what you would do is you would take the x value here and you'd replace it with whatever the negative was, and you'd come over here. Okay, and the distance from the y-axis would be the same. You'd just be at the negative value over there. So when you're computing reflection across the y-axis, you replace the x with negative x. Okay, so we start off with our function in blue here, and if we replace x with negative x, then we reflect across the y-axis. And it's just like what I was telling you, right? So if I started out at the point 1, 2, and I replace the 1 with negative 1, then I go right across the y-axis, right? The same distance away, just reflected across that y-axis. Okay, so that's what's going on with a horizontal reflection. Okay, so you just replace the x with negative x. And it's like a composition, right? We're just composing it there with negative x. Everywhere you see an x, we replace it with negative x. Now, a vertical reflection is a similar sort of thing. Now what you do, instead of replacing x with negative x, you replace y, whatever this y value is up here, with the negative of that y value. And that'll flip you down from being positive to being negative. And the way that we do that is, remember, f of x is equal to y, so we just compute negative f of x. Okay? So here, if we multiply the x by a negative, that's a horizontal reflection across the y-axis. And if we reflect across the x-axis, it's called a vertical reflection. That's when we replace the function with negative f of x. So let's just do a quick example so you can see how something like that's done. Here we're starting with this function f of x is equal to x minus 1, absolute value. And in your mind, we should sort of think about what this graph looks like. So it's that v that we had, and the minus 1 is going to shift you to the right by 1 unit. Okay? So you could just sort of sketch the graph really quickly. It should look something like that. Right? Just a nice little v moved to the right by 1 unit. And what we would like to do in this case is reflect it vertically. Which is what's called reflecting across the x-axis. And then we'd like to reflect horizontally, which is reflecting across the x-axis. If we want to reflect across the x-axis, we replace y with negative y. So negative f of x. And if we want to reflect across the y-axis, we replace x with negative x. So we get f of negative x. Okay. So these are two separate problems. This was part A, and this was part B. And you should imagine what the reflections sort of look like, right? So if I were going to reflect this thing around the x-axis, it would come down, right? So it would look like this. So that's what that guy would look like when we reflect that down. And the equation for that would just be take this whole equation and multiply it by negative 1. So it'd be negative absolute value of x minus 1. Okay, so there's the equation that we get for reflecting this thing horizontally. And typically we would do something like y equals, but just be careful with, infinity, how they're asking you for the format. They may ask you just for this piece here. And then over here, if we want to reflect across the y-axis, right, this point here is going to come over here to negative 1. And this whole thing is going to look something like that. So let me do that in yellow. So here in white is our original function, and orange is what happens when we reflect this way. Yellow is what happens when we reflect around the y-axis. And if we want a formula for it, all we do is everywhere we see an x, we replace it with its negative. Okay? And this equation now is this one in yellow. So let's at least see that in Desmos so that it's not just me drawing lines on the board, and you can see a graphing calculator actually do it as well. So here, let's just start up with not this guy, but the absolute value of x. So there's our v, and we're going to want to move that thing to the right by 1, so subtract 1 from the x. There it is, moved to the right. And then now, like we said, we want to flip it so that it's down here, and we can do that by just taking the negative of that. There we go, and we should probably do a different color so it looks a little bit different. Orange. Okay, so there we are. And then if we wanted to instead reflect it across that y-axis, we would just take the x here and replace it with its negative. So there it is in red. Okay. So again, this point gets reflected to this point over here. This point, for example, at 3, 2 is going to get reflected all the way over here to negative 3, 2, right? And this point right here at 1, 2 is going to get reflected to this point here at negative 1, 2. Get to the negative 1. It's a little bit off there. Anyway, negative 1, 2. Okay, so that's the picture that we have in Desmos. Same sort of thing that we just had. Okay, so that's what's going on with the flipping vertically and horizontally. You either replace x with negative x or you replace y with negative y. Now, some functions will have the feature that when you try to compute this, right, or this guy as well, that they're exactly the same. Okay? And what that means is that they have what's called symmetry. So this is where the definition of even and odd comes in that I was mentioning to you before. And I'll tell you why the terminology is even and odd, but let's just look at the definition first. So somebody gives you a function, and what you want to do is reflect that function both across the y-axis and then both the x and the y-axis. So this is first rotate across the, or I'm sorry, reflect across the x-axis, and then this negative on the outside means reflect across the y-axis. So this is two reflections on this one, okay? Negative f of negative x. The function is what's called even if this f of negative x is the same thing as f of x, okay? And the function is odd if f of x is the same thing as the negative f of negative x. And if neither one of these things are true, we just say that the function is neither even nor odd, right? So functions are either even, they're odd, or they're neither, just like numbers, right? So you could have like a number like 1/2 is neither even nor odd, but it's still a number. Okay, so these are the definitions, and they mean something graphically. So let me go back to Desmos and at least show you what they mean graphically and where the names come from, okay? Because there's two specific functions that are even and odd, and this is where the terminology even and odd comes from. So the first function we'll look at is a familiar one, the quadratic f of x is equal to x squared. Okay. And again, so the way you do this, you just plug in values. If I plug in 1, I'm going to get a value of 1. If I plug in 2, I'm going to get a value of 4, and so on and so forth. So I've got my parabola here. And you'll notice that if I were to reflect, say, this point here at 2, 4, so this is the point, I could just type it in, so 2, 4. So this is the point 2, 4. And if I were to reflect it across the y-axis, what I'm going to do is replace the x with its negative. So negative 2, 4. But you'll notice that that's also on the graph. Okay? So if I take this graph and I try to reflect it across the y-axis, I just get the same graph back. Okay? I get exactly the same graph back, and you can see that by computing something like f of negative x. And you can see that it's just the same thing as this one in purple. And this has algebraic significance as well, right? So this just means negative x squared is the same thing as x squared, right? That's essentially what we're seeing here. This is f of negative x, and this is f of x on that side, and they're equal to each other. So that's what we're seeing with this, and we're seeing symmetry across the y-axis, right? So when a function is even, we say that it's symmetric across the y-axis. Let me show you another function that has this property. Cosine of X is another function that has this property. If I look across the y-axis, everything is symmetric, right? This guy matches with that one, this one matches with that one, and so on and so forth. But there are some functions that don't have this property. Let me look at, for example, something simple like x cubed. Okay, so here, if I reflect x cubed across the y-axis, right, this point, for example, here, is going to come over to this point there. And that's not on the graph anymore, right? So this black function here gets reflected to this purple function there. And then what we can do is apply the transformation, where we reflect across the x-axis instead of the y-axis. And if we do that, we'll get negative f of negative x. And you'll notice we get back to the same function that we started with, right? So this function is the same function as that one. And what we're seeing here is the fact that negative x cubed is equal to x cubed. But these two things are the same. And this is what we mean by an odd function, right? So if it has this sort of symmetry, and there's another nice trig function that has this property as well. If I look at sine of x, if I reflect it around the y-axis and then the x-axis, I get back to the same function. So here it is reflected around the y-axis, and then you reflect that purple one around the x-axis, and you get back to the black one. But there are some functions that are neither. Some functions don't have any of these properties. Like we can look at something like 2 to the x. And if you look at 2 to the x, f of negative x is this function in purple, not equal to the original function. And then if I take that function in purple and reflect it across the x-axis, I get this thing down here, which is also not equivalent to the original. So this would be a neither function. It's neither even nor odd. Now just going back, where does the terminology come from? Well, again, x squared is, x squared is an even function, and the exponent is even. And x cubed was an odd function, and the exponent is odd. And in fact, the same thing is true. If you change this to any even number, it's going to be an even function. If you change this to any odd number, it's going to be an odd function. But anyway, that's where the terminology comes from. So let's do an example of the type of thing infinity will ask you to do. Okay. So it has a nice geometric meaning, but in addition, you can just sort of check it with the definition. So we'll do that now. But before I do that, let me just do the how-to, right? So just so it's broken down for everybody. Somebody asks you to determine if the function's even, odd, or neither. And what you're going to do is you're going to compute f of negative x. You're going to compute the negative of f of negative x, and you're going to check to see if they're equal to f of x. If this first one is equal to f of x, then it's even. If the second one is equal to f of x, then it's odd. And if neither one of those things are true, then you hit a neither. Okay? So that's just basically what I was saying before. And we want to compute both of those values. So let's go through and do an example to determine if the function is even or odd. And in this case, I'm going to do this guy. So the task here is f of x equal to x cubed plus 2x even, odd, or neither? Okay, so we've got our function, and it's equal to x cubed plus 2x. Okay, and in this setup, what we want to do is we want to compute f of negative x, and we want to compute the negative of f of negative x, and we want to compare them to see if they're the same thing as f of x. Okay, so here, let's compute this. Okay, so you should check to see if it's even first. This is a little bit harder to compute, and if you get a yes answer for this, then you're just done. So start with the even question, and here, everywhere you see an x, just replace it with negative x. So this is equal to negative x cubed plus 2 times negative x. And negative x cubed, that's 3 negatives, so it's the same thing as negative x cubed. And this one is 2 times negative x, so that's minus 2x. Since f of x does not equal f of negative x, the function is not even. Okay, and we wouldn't even need to write that in our supporting work. We would just sort of do that on the scratch side paper, right? And we just say, okay, it's not even. And then we check to see if it's odd, okay? So in this case, we want to compute the negative of f of negative x. So here we would compute the negative of f of negative x. So that means we have a negative on the outside, and then basically this expression here, right? So we're plugging in everywhere we see an x with negative x, so we would get negative x cubed and then plus 2 times negative x. And we want to ask ourselves, does it actually equal the original function? Well, this calculation is the same. Inside of those parentheses, you're still going to get now negative x cubed minus 2x. And then distribute the negative sign. This is a negative times a negative, that gives you x cubed. That's a negative times a negative, that gives you plus 2x. And indeed, yeah, it does actually equal f of x. So this function is odd. And we should expect that if we were to graph this function, right? So if we were to graph this function x cubed plus 2x, then we would see the symmetry that we were talking about before. If we reflect it across the x and the y-axis, then it should be the same. So here it's x cubed plus 2x. Okay, so there's that function. We could flip it across the y-axis first. So here we're going to flip it across the y-axis, f of negative x. Oops. That's the equation that we got over here, right? So we had that equation for f of, over here, f of negative x, and it's not equal to the original function there in red. But then we computed the negative of f of negative x, and we found that, yep, it matched up with the original function. So remember, the original function was there in red, and we got this function in blue. So that's what we figured out, and so therefore it's odd. Okay, so we reflect around the x and then the y, we get the same function. This is called odd symmetry. Jordan, it's either even or not even, and then odd or not odd. And if it's both not odd and not even, then you go on to neither. I'll give you an example of a neither. Right? So here's an example of one that's neither. Sorry, hold on. There we go. So this guy here, s to the fourth plus 3s squared plus 7. And this one's going to be neither because of the plus 7, right? That plus 7 is really, I'm not even going to do it on the board here because I think we need to get on to the next topic. But this plus 7 is really going to throw things off, and you're not going to get either one of these calculations to work out. So if it's not even and not odd, then you would write down that it's neither. And this is an example up here, this one up here in the box. That's a neither. Okay. So last thing that we need to talk about is the stretching and compressing. And there are two types of stretching and compressing that can happen. You can compress vertically or stretch vertically. So stretching means that you're making it sort of longer and pulling it out. And compressing means that you're sort of pushing it together, right? So let's look at this picture so we can sort of see what we mean. We start out with this blue function here. And when we're doing vertical stretches or compressions, we're taking the function and we're multiplying it by a number. So for example, we'll look at something like 2 times f of x or 0.5 times f of x. If this number is bigger than 1, then what's going to happen is everything's going to get larger, right? So if it was 2, you're going to get 2 times 1. If it was 4, you're going to get 2 times 2. It's going to get even bigger. The larger it is, the bigger it will get, right? And so what we'll get is this stretching up of the function. And it's going to be more elongated the further away you are from the x-axis, right? Because multiplying by 2 further away from the x-axis is going to make it even further out than something that was closer in. So that's what they're saying here. If I multiply f of x on the outside by a, and it's a number bigger than 1, then the graph is going to get stretched out. And they talk about factors in the book and stuff like that. I wouldn't worry too much about it. Just remember that if the a is bigger than 1, things are going to get stretched out up higher, okay? Now, if the number is in between 0 and 1, for example, like a half, well, then it's actually going to get smaller, and that's what they mean by a compression, right? So if I take a number like 2 and I multiply it by a half, I get down to 1. If I take a number like 10 and I multiply it by a half, I get down to 5. So in those cases, we get some vertical compression, okay? Now, you really only need to think carefully about what happens when a is positive, because if A were ever negative, then there's really a vertical reflection going on as well. So you'd have to take care of that negative sign as a reflection, okay? And then you think, okay, what's the absolute value of that number, and if it's bigger than 1 or in between 0 and 1. That tells you if it's a stretch or if it's a compression. And I'm going to open up Desmos here in a minute. We'll see graphs sort of stretch and compress, okay? So that's vertical, and you multiply it by the f of x. And then similarly, when you want to do it horizontally, you multiply it by the x. So this is where you have f of b of x, right? So not on the outside of the function, but on the inside. In this case, things are backwards, just like they were with the adding and subtracting. Now, if b is bigger than 1, the graph will actually compress. And it's not going to compress vertically, it's going to compress horizontally, right? So if I do 2x squared, this thing looks like this now. It goes from the blue one now to this sort of like teal colored green one here. Right? So I went from x squared to 2x squared. If the number is in between 0 and 1, then the graph is going to be stretched out further horizontally, okay, pushed out to the right, like this. And if the number is negative, then it's really actually horizontal reflection. So you should have thought about it as a reflection in the first place. So I'm only really going to care about these two things for you, okay? So think about what happens by b. And notice it says by 1 over b. Don't worry about the 1 over b. Nobody's going to ask you any questions about how much the compression is happening. But what you need to know is that this is what's going to happen, right? And there are questions in infinity where they ask you about how, what's the value here? Is it a, compression, or is it a stretch or something like that? And you'll just go through and identify if the number's in between 0 and 1, or if the number's bigger than 1. Okay, so that is all of it for our learning objectives, right? So vertical, horizontal shifts, reflections across the x and the y-axis and how those work, the idea of even, odd, and the concept that it could be neither. We just talked about compressions and stretches. There's only a couple of questions in Edfinity on those, but not as important as these other topics. And then we did a lot of combinations, right, of all of this sort of stuff going on together. Let's just end the class with a few examples. Here we're going to describe how the graph of the function will be transformed. And we don't even need the function itself. So let's go through and do that here. So here we got x minus 49. Is this up or down, left or right, and by how much? And we'll just go through the chat, and once people put it in, then I'll tell you what's the right answer. Okay, so we're subtracting 49, so it's going to the right. Okay, subtracting 49, and it's 49 units. What about the next one? Left, 43 units, right? Because we're adding 43. These are all on the inside of the function, right? The inside of those parentheses. What about this one? Okay, left 3, and this one? Right 4. Okay, so now notice the difference, right? So now we're adding to the outside. So what's this one? What's the difference here? The up 5. This one? Up 8 here. Down. This one. Down 7. Okay, and then this is a combo one, right? What's going on here? We've got two things going on, this minus 2 and the plus 3. Where are we going there? Right, 2 up 3, good. So first quadrant, right? And then last one. Okay, great. Plus 4 means left. Yeah, left. And then up, oh, I'm sorry, down 1. Minus 1 means down. Awesome, guys. Have a nice day. And remember that we're not going to cover anything on 3.6, so come in on Monday with questions if you have questions about it.